What's up, guys? It's Andy, and I'm still sick, but today we're gonna keep on going, and we're gonna do something called we're gonna do implicit differentiation. I call it variable juggling because you're basically juggling around variables to differentiate something. So what is it? Well, let's say we got a strange function like this, and I say strange because it's not like y equal to something x or whatever. No, you got x, y equals 1. And this, you're probably saying, well, you just wrote it that way to piss me off because I can just divide by x over here and y equals 1 over x, and then I could just differentiate it that way. But that's not the only way to do it. Just give me a second. Alright, there are two ways to solve. So one of them is the way that I just showed you. You just divide by x. Y equals 1 over x. Derive that, so x to -1, -1, x, -2, so that's just -1 over x squared. That's y prime. But if we're feeling lazy and not like juggling that around, here's another way. Alright, so realize that this, if we're not going to do anything, that's the product rule right there. So that's x. Now y, what is the derivative of y? It's, we can just call it dy dx, derivative of y relative to dx. And then plus, alright, derivative of x, that's just 1. And y, we can just write y equals 0. Alright, so now we're going to subtract y over, so we get y equals x dy dx. And dy dx is just y prime. So why don't we just juggle it over, divide, and we get dy dx equals y over x. Now recall that, if we juggle this a little bit more, we get y equals 1 over x. And, that's supposed to be a negative y, by the way. Alright, so negative y over x, and if we substitute y equals 1 over x for this, we get -1 over x, and we get -1 over x squared anyways. So this little substitution, that's implicit differentiation. Woo! Whoop. My sound effect budget is pretty low, so that's why I did that. So, implicit differentiation, using a placeholder for y prime to differentiate complicated functions, or, as I call them, weird. So, let's go into this one. Now, this one right here, I mean, you probably could juggle it around and you got, y squared equals 1 minus x squared, and do something like that, but then you end up with a square root, and square roots are messy, so I tend not to deal with that. And by the way, just now that I think about it, this is a circle equation. So how do we start to differentiate this? Well, we can just derive both sides. So 2x plus 2y. Now, because we derived that, we need dy dx equals 0. Alright, pretty straightforward, but now we want to get this one over there so we know, what that is in terms of dy dx. Or, no, how we know what dy dx is in terms of x and y. So, I'm just going to subtract 2x. So, 2y dy dx equals -2x. And now we can just do that over. So, dy dx equals -2x over -2y, or just x over y. And that's how you find the slope, a tangent line to a circle. Anyways, now we got an even wackier function here. So x to the third y plus y squared x plus 8 equals 42. Well, we again derive both sides, but this time, because I'm an asshole, I threw two product rules at you. So, let's see.
X squared? Yeah, I just realized that by doing this I'm hurting myself more than I need, because you guys can just watch me do it, but well, that's enough. I just So y x squared dy dx plus 2y x dy dx plus y squared x equals 0. So we're just going yeah, okay.
Yep, looks good. All right, so now we need to figure out how to get dy dx by itself, and we can just move it over to one side. So why don't we just keep it positive? Dy dx, I'm just going to factor it out, saves a few steps. Plus 2yx equals 3x squared y plus y squared. And this should all be negative. And now we can just divide dy dx equals negative 3x squared y minus y squared over x third plus 2yx. And I'm just checking to make sure that I did it correctly. Alright, yep, I did it correctly. And now just to cap it off, something that's kind of like the first one. Just y equals 5y squared plus x squared. Well, how do we do this? So dy dx equals 10y dy dx plus 2x. Okay, we got that. And now we're gonna shift this over, so negative 10y, and notice that that's just a 1 dy dx. I factored it out on the way there, equals 2x. And now we can just do dy dx equals 2x for negative 10y plus 1. And so that's all I got for you today. Just remember that implicit differentiation is taking the derivative of a variable you wouldn't normally expect to take the derivative of, and then juggling it around so that way you eventually get a equation that looks pretty friendly. You know, like it's a way to derive functions where y is where it's not supposed to be. Just think of it like that. Hey guys, just one quick thing that I forgot to say at the beginning of the video. The reason why we do this, the reason why this is possible, the reason why you can write y dy dx is because when you differentiate, let's say y, well, you derive it, you gotta use the chain rule to figure out what the derivative of this thing is. So that's why we do it. So let's say we got, x 25y equals 1. Well, we're going to do product rule first, so that's just going to be x, well, I'll do it backwards. 25y, no x plus, all right. And now we got the x, but now we need to take the derivative of this. So that's just going to be times 25, and derivative of y, we don't know that, so we put in y prime, which is equal to dy dx, so we'll just put it over there. But as you can see, it's the chain rule. That's the derivative of y. So the reason why this is possible, it's basically, if you think about it, it's basically the chain rule. Now, I wasn't taught that in high school, but I just looked it up to make sure, in post-production that I was doing everything correctly. And yeah, it's basically a variation of the chain rule. So I guess you really do have to chain rule everything. That's all I got for you. Peace out.